Hello, this is the next video in a playlist that I'm calling General Linear Models 1. And here we're going to look at the simple linear regression setting, and we want to test whether the model is useful or not. Now, doing that in simple linear regression is a little bit different in multiple linear regression, and we'll get to that in maybe 20 videos. But here are simple linear regression. So our model is this. So it basically X and Y follow a line with some fluctuation. So for example here, so if it fluctuates around this line, and in this case the slope is not zero, and we're saying that model is useful, because if the X is a little bit low, then we're going to predict a Y here. If it's a little bit higher, then we're going to predict a Y up here. So it makes a difference. Now when the slope is roughly zero, we say the model's not useful, because whatever X you pick, you pick the same Y. And so there's no benefit into having, using X to help us predict Y. And so ultimately we want to test whether the slope is zero versus the slope is not zero. When the slope is zero, it says the model is not useful. When it's zero, it says this X variable is not needed to help predict Y. And so the beta 1 not equal to 0, the model is useful. So we need a couple pages of background first, unfortunately, and then we'll get to the main result. So first of all, and I'm going to try to do this a little quicker, because you can pause the video and go through the math yourself and actually comment whether that is helpful or not, meaning go through the video faster to get to the main result, or actually slow down and go through all the background and derivations. So here we want to show that h1 is equal to 1, and this is a 1 vector. It's a constant of ones, and H was the hat matrix defined like this. And so essentially, to prove it, you just start listing the things. So this is H and that's 1, this is H and that's 1, and you just go through the derivations. This X transpose X inverse we showed in a previous video that it was this, and you go through the math and you get 1. Now we also want to show that J times the 1 vector is equal to the 1 vector, where J is defined like this. It's essentially a constant matrix with elements 1 over n everywhere, and that's an easy proof. J times 1, you plug in what J is and then 1, but 1 prime 1 is n, so the n's cancel, leaving just 1. We want to show that H minus J times the 1 vector is 0, and here it's just plug it in and then take 1 times each of those and everything cancels. Now let's derive the least squares estimator for beta 0 when our model is this. Okay, so this means that beta 1 is 0. If beta 1 is truly 0, then this is the model that we're using. And what does that mean we're using to help us predict Y? And that's, we're going to look at the least squares estimator. Notice that in matrix form, this is scalar form and this is matrix. The design matrix is a column of 1s and with the beta 0. If beta 1 is not 0, then this design matrix is a column of 1 and a column of x's, and then we have beta 0 and beta 1 here. All right, so let's find the least squares. So we want to sum the squared errors, but the error term, if you subtract the beta over, is this. Take the partial derivative, the 2 comes out front, you reduce it by 1. Partial derivative of beta 0 is minus 1. We set it equal to 0. Multiply everything by minus 1, divide everything by 2, and we're left with this. Take this over and divide by n, and we get beta naught is y bar. And that kind of makes sense when you don't have any variables to help predict y. Why not use the average? you know, because on average you're going to be correct. And so that's it. But when beta 1 is not 0, then we get the regression line. And so to me, it seems intuitive that somehow we're going to compare the least squares regression line and y bar to see how well the model fits, right? If this model does better than y bar, you know, what we'd use if we didn't have any variables to pick, well, then the model's useful. Okay, so keep that in mind. As a reminder, the sum of squares regression, which in matrix notation was this, was a non-central chi-squared with this non-centrality parameter, call it lambda. Now, under H naught, so that means that we assume that beta 1 is truly 0, then this non-centrality parameter, the design matrix X, is really just a column of 1s, and beta, which is normally beta 0 and beta 1, is just beta. The same, right? The model development up here. But if you look at this, H minus J times 1, we said was 0. So under the null hypothesis, the sum of squares regression becomes a central chi-square distribution with 1 degree of freedom, right? The non-centrality parameter is 0. Now, this result, we want to show that the sum of squares regression, which as your reminder is this, it's the fitted value minus y bar squared summed, is this. So you take this quantity, put it here. Now you write what the least squares line is, which is this. And then the least squares estimator for beta 0 is y bar minus beta 1 hat x bar. So the y bars cancel. You're left with this. Now we can factor out a beta 1 and then take it out of this squared, but it's got to come out squared. And then what's left over is this, which is SSX. So it is proven. Now the last page here, we can start talking about the main result. So in previous video number 3 in the list, we determined that the beta 1 hat, the least squares estimated for beta 1, is linear in the y's, thus normally distributed, right? Because we're saying the y's are normally distributed. And it's a linear combination of independent normally random variables, so itself is normal. So the expected value is beta 1 we showed in PV3. The variance was this. So beta is normally distributed with beta 1 mean and sigma squared over SXX for the variance. Now, so if we subtract the mean and divide by the standard deviation, then this becomes a standard normal distribution. So you invert and multiply, that's what this is. Beta 1 hat, beta 1. So it's standard normal. So this, to me, seems like a good test statistic. And actually, it is a good test statistic. And in 2 videos, we're going to develop tests based upon this quantity, which ends up being a t-test statistic, but that's for a later video. So let's square this quantity, z squared, and we get this, right? So this is squared, that's squared, and this quantity is squared. But under H0, beta 1 is 0. So this is 0, which then says z squared is this, right? And we just showed that beta 1 hat squared times SXX is the sum of squares regression, and this is chi-squared 1. So now this is our test statistic right here. But wait, how can that be our test statistic? Because we don't know sigma squared. Well, why don't we just put an estimate in for sigma squared? We could, and then it becomes approximately chi-squared with 1 degree of freedom, right? Because we're adding another variable. But so maybe if we put in the estimate for sigma squared and then figure out this overall distribution, maybe we can just use it as our test statistic, and that's what we do. So in PV8, previous video 8, we showed that the sum of squares residual was a central chi-squared with n minus 2 degrees of freedom. We also showed that the sum of squares regression is independent of the sum of squares residual. So the test statistic for beta 1 equal to 0 versus beta 1 not equal to 0 is this. Okay, so this is our sum of squares regression right up here. And then what we do is we put an estimate in for this. So it looks like we're just sum of squares regression over the estimate. But it sort of right here. So the mean square error. So sum of squares regression divided by 1 is actually sum of squares regression, but they call it the MSR. And then this is MSE, the mean square error. It's our estimate of our data. It's like this. But if you do it in steps, this is chi-squared and this is a chi-squared, divided by the respective degrees of freedom. They're independent, so it becomes an F test statistic with one numerator degree of freedom and n minus 2 denominator degrees of freedom. And so this is our test statistic. But actually, this is what was in our ANOVA table in the previous video. So in a sense, we are comparing y hat, which is, and y bar, which is what is in this MSR. We're comparing them via this sum of squares regression. So we use the ANOVA table to conduct the test. And actually, let me pull out the previous video. I want to flash that. See if I can do it quickly. So here was the ANOVA table that we discussed. And so this development was, we just developed this. And so that p-value will instantly tell us whether the model is useful or not. And so in the simple linear regression setting, that is equivalent to testing beta 1 0 versus beta 1 not 0. Now, it always seems a little confusing to me that, well, it did initially, that, I developed, that why go through this, where really we just want this to be the test statistic, SS regression over the sigma squared, as we want that as our test statistic. Right here. And then why can't we just plug in sigma squared, or an estimate for it? Well, that changes the test statistic. There's more randomness. So then we have to figure out the distribution, but this is actually, it almost looks like we're just plugging in our estimate for sigma squared, right? But you kind of have to go backwards and figure out that's a chi-squared, this is a chi-squared. You get the sigma squareds to cancel, the unknowns, and then what's left we can calculate. So the test statistic is this. Well, that's all I have for today. Hopefully you enjoyed that. I sure did. That's it. Like the video and subscribe so you don't miss the next one. Thanks. Bye.